Right. As you're all probably aware, I'm fiercely proud of being an engineer amongst quality scientists. So today we're going to get my view of liquid crystal optics. It's nothing to do with Schlieren textures or beautiful distillations or all sorts of lovely pictures. This is more about how I see liquid crystals as optical elements and how I use them to make devices. And so it's actually a very simple talk, and it's clicker-tastic, so be prepared for some hastily edited, improvised content. I apologise now if my answers are wrong, because I only did them while I was watching Julia's talk. Right. Whoops, that's not good. What the heck's that? Let's try that again. This is something to do with the clicker thing. Don't want you. Why would I not let you go to another slide? I have to click the screen. There we go. This is the blank slide now. It's not good. There we go. And sorry, I just have to turn this off on the other version, but now I've got the clicker thingy on. Just give it these irritating animations. I'll watch me here all day. Right, so I'm going to focus on two things. I'm really going to focus on one thing. The first one, although scattering is very exciting, very interesting, and is a very large and historic part of liquid crystal research, to me it doesn't offer something that's terribly useful. I'm trying to make devices, particularly displays, holograms, correlators, all sorts of interesting things where I can manipulate the optical properties of light to create useful applications. And scattering really, it kind of messes things up. It destroys the wavefront, it destroys the phase, and so that really is a very difficult thing to use in a lot of applications that really require that information. Whereas the birefringent, you know roughly what it is after the first few talks today, is a very useful thing. This gives me the ability to retard a wave, it gives me the ability to change its speed and vary its propagation. And particularly if I have 2 pixels, I can vary the propagation of one pixel with respect to another, and that's a very powerful tool indeed when you're talking about applications like I am. So very quickly, a bit about scattering. This is courtesy of Wikipedia about 4 o'clock in the morning. It's one of the most oldest exploited liquid crystal phenomenon, and essentially you take a wave and you hit a particle or a structure of some sort. It could be a liquid crystal molecule or a clump of molecules in some way. They may be twisted, they may just be uniformly aligned. The light gets essentially disturbed by that clump and is scattered in a random direction. And that's the problem, is the random element of scattering that makes it rather difficult to use in lots of coherent and interesting applications. And just to give you some reference, this historical mysterious figure called alpha comes up, and you can classify the type of scattering, which really comes down to the size of your particle, your structure that you're scattering from, with respect to the wavelength of the light. So it's much less than 1 we have Rayleigh scattering. If it's about 1 we have Lie scattering. Most of the effects you see in the crystals are Lie scattering effects. And if it's much larger, then you have geometric scattering, sort of brute force scattering if you like. That's really all I'm going to say about scattering. It's really just a reference, because in my applications it's not a terribly helpful or useful property. So just to give you some ideas of how this is manifested in liquid crystals. You've already seen PDLCs, the nice chap who applied his face behind the screen here in the first lecture. That was a polymer dispersed liquid crystal. It's a polymer matrix with little globules of liquid crystal that you align or left in random states. And that either passed the light through in the clear state or scattered in the random state. And that was quite a simple system. You also saw reference to cholesterics, correlatics, photoconics, all sort of named roughly for the same kind of thing. Sometimes they're wanted, sometimes they're unwanted scattering states. They have a beautiful cholesteric texture, lovely colour properties. Then you hit it with the wrong field at the wrong time, with the wrong following wind, and bang, it goes into the photoconic state, and it goes completely random, and you get all these little helices bundled up in little chunks, and that scatters the light in a annoying fashion. Symmetric A, we've also seen pictures of this morning, that has a random scattering state, and that can be made very useful because it can be made bistable. You can lock it into a scattering state, and it will stay in that scattering state, you take the field off, and it remains permanently written. And that's very useful for things like electronic windows, spark glass, and that's a big area of interest in the university environment. Sorry for my spelling of alignment there, it was earlier early in the morning when I was adding this particular section to the talk. And something also you've seen quite a bit of this morning are various types of hydrodynamics and active systems. And this gives you essentially turbulence or some kind of flow within the system, and that can also be used to interact with the light and scatter it in a helpful fashion. And actually this is almost looking like it might be useful in some areas, and so I still have a vague interest in EHD because it may be enough control in the system because of the way the actual flow motion works that we can actually harness that effect in a useful fashion. And as was pointed out yesterday by Tim, actually scattering is one of the very first successful display demonstrations. It was dynamic scattering from RCA. We saw this chap in different pictures yesterday, areas with his actual display. However, it does link to this EHD effect, therefore it requires ions and currents to drive it, and therefore is not a terribly efficient or easy display technology to manufacture or produce in large numbers cheaply or efficiently. So it never really took over the world. It was very interesting and very exciting at the time because there's nothing else like it. But eventually things like systematic and other effects came along and took over from those sorts of devices. So scattering has had its place, but never quite made it into that display world. As I've mentioned already before, these effects, PDLCs, can be used to switch windows, switch gauge, for smart glass systems, and this is an example of actually one of my own samples. This bit in the middle, this is something that I was experimenting with nanotubes, but this rather nasty looking mushy bit down the outside, which is not a very nice looking texture, is a photoconic texture, where essentially you've got a random alignment of helices, little pieces of crystal helical structure chopped up into bits, and they're essentially scattering the light and creating this rather lovely beige texture here. Just as a reference on smart windows and doors, I have a lovely picture of, this is a bit, sounds a bit weird. If you go to Amsterdam, there's a very lovely museum, I can't remember what it's called, but it's got the Vermeer night watch painting in it. And downstairs in the restaurant are toilets. And those toilets have PDLC screens. And I was just, this is like, cool, this is liquid crystals in the real world. I'm going to take a photograph of this, so I'm standing there in a public toilet with a mobile phone, trying to take a picture discreetly of a screen. And of course, the things don't work by switches. They're controllable when you open or shut the door. So you have to go into the cubicle in order for the screen to activate. So I of course then have to scratch my head and like, wait, somebody else. That's going to look really bad. Or I can go in myself and take a picture. So I took the option B. Unfortunately, in the picture, there was a reflection of me taking a picture, and it just looked really, really disturbingly sinister. So I decided not to show my early side of my public toilets. But I suggest you go over there and have a look at them. They're really cool. They're very clear, and they're in their clear state, and then as soon as you shut the door, bam, they're in that white opaque state. Although, I don't know, there's still a bit of, bit of a silhouette going on there. I'm not quite sure how private they really are. This is Europe, so, public toilets are places of exposure. I'll just show you this. This is one of my own devices. It's actually a carbon nanotube device, but it does show some very interesting electro-hydrodynamic effects. These little dots are carbon nanotubes actually pointing out of the screen, acting as electrodes, and then if I apply a field to this particular device, I get this very strange effect indeed. Maybe I don't. I used to. It's not going to behave for me. Plan B, when in doubt. Improvise. As an engineer, always have a backup plan. It is the media player, there it is. So it does this kind of wobbly thing. And as I increase the frequency, this is low frequency AC signals, take this field off, that's what it looks like in a steady state. And you get these really strange disturbed effects, and that's kind of the large scale version. If I show you the small scale version, this is the high magnification. You can see there's the little random states. As I increase the frequency, they get more and more random, and then bam, they're really random. This is the sort of scattering texture that you get from the electro-hydrodynamic effect. That was what was actually controlled and harnessed in that earlier display I showed you from RCA to give you a visible contrast. This particular device obviously does not have any ions in it. It doesn't require any current to drive it. What is actually causing the EHD? We don't really quite know, but it's something to do with these strange structures that are projecting from the surface of my sample on a 10 micron pitch, which at a particular frequency just happen to give you these very, very unusual hydrodynamic structures. So there's something about the electric field profile that's causing this to work. And really I don't know or understand why it does it, but it looks very, very effective when you see it. I wonder why that didn't work. Anyway, who cares? Onwards and upwards. So here's your first. Oops, something's missing here anyway. So my first section is really just to give you an idea of optics and how the engineers view optics. I'm going to go through this fairly quickly. So I'll give you a rapid tour of the optics you need to understand by modelling. So here we go, vote now. What is your favourite sort of matrix? Is it, excuse my spelling, because I had to do this in a hurry during the previous lecture. Is this a Derivative matrix? Is it a Muller matrix? I think that's spelled wrong. There's another E in there somewhere. I'm not quite sure where to put it. That's not as a Muller light yogurt, by the way. That's as a Muller matrix. Is it a Jones matrix with the hinges and the big title at the top? Or is it the film matrix? Of course, it's everyone's total vote, but there's only 47. Of course, my vote to do it, rather than the 47. That's stop. Oh, 48, hey. Oh, that's weird. And, well, that's what I call a really even distribution. That just shows indecision at its best. I'm glad to see that the sensible amongst you, probably near to being engineers, as you can be, voted for Jones matrix. People that also find Berman and Muller, they're very powerful, they're actually too powerful in a way for what I want to do with my optics, so they really do other things that aren't really required. They have extra indices, they have extra features which aren't really useful for my kind of analysis. The 6 people that voted E, I'm sorry, there is no E. You should be shocked. That is just not acceptable. Please stay within the bounds. All of my clicker-ometers have only 4 choices, so E is not an option, as they say. So of course next is going to be all E, but never mind. So yeah, sorry about that. Yes, as you rightly selected on a majority, the Jones matrix is by far the most exciting matrix for the average engineer. Why? What the heck? Go away. I think we're going to click on the background and then, there we go, yeah, I've sussed it now. Why is it interesting? Because it tells me the propagation of an electromagnetic wave in a very simplistic, non-Maxwellian, non-nasty maths, no hard differentials way of understanding. So I have essentially a wave, I represent it as a nice sinusoid, and that's just purely for pictorial value, could be any shape you like. What it does have is an electric field plane and a magnetic field plane, and they are orthogonal to each other, and they propagate in the z direction. That's what we call polarization. That's what Jones matrices tells us how to analyze. So we can break that into 2 electric field orientations, our vertically polarized orientation, our horizontally polarized orientation. They form an orthogonal set of eigen states, and therefore I can now represent any generic polarization state. And I can go all the way to the Poincare sphere if I want to really complicatedly pictorize this. For most things I can understand quite simply the propagation of light from those 2 principles. And all Jones matrix does is tells us how to mathematically represent that. So we have a 2x1 matrix where the upper element represents the horizontal component of those eigenstates, and the lower value represents the vertical component. And as I add and subtract bits of those 2 components to make up any arbitrary orientation of the electric field, I add and subtract those 2 parameters in my Jones matrix. That's why I like it. It's really simple. It's only got 2 numbers, so it's really nice and easy, whereas the Berman and the Muller, they have other numbers down here, which do really scary things. And are really quite useful, but not for me. So for instance, I can represent 45-degree linear, this is the electric field is tilting out from the axis like this, by essentially a component of the vertical and a component of the horizontal, and to get 45 they have to be the same amplitude, and therefore I get this nice sum of the 2, which represents 45 degrees linear state. And if the world was linear, it would be lovely. However, the world is not linear, we have to add more information to the system, and that is the phase between these 2 eigenstates. They don't have to start at the same point on the point on the y-axis. Therefore I add e to the j phi term, where phi is essentially the phase delay between the 2 states, and that gives me another whole bunch of different polarization states, which now relate not only to the 2 eigenstates, but their relative phase between each other. And these are called the elliptical or circular polarized states. And these are the ones that are really hard to draw and get your head around. I'm afraid. But here's a good example. Here's a circular elliptical state. I now have a phase lag of phi between the two eigenstates. And therefore, if you actually simultaneously plot the director or electric field, at any point here, you can see I have 0 of the red and all of the green, so the E is pointing up. Here I have 0 of the green and all of the red, so now E is pointing across. So as you follow this down, you add up and find what it does is it goes round in a sort of a spiral as it propagates along as an axis, hence why it's called circular or elliptical. So if you look at the end of this axis, you see this electric field vector going round and round and round this circle in a timely fashion. And if they're the same height, you get a circular state. If they've got different relative heights or different relative phase, you'll get elliptical states of various orientations. And that's why they're called elliptical. And they can also go in the clockwise or the anti-clockwise, or left-handed and right-handed circular states. I'm not going to go bore you with the conventions here, as it can take all day, but they're very useful for analysing all the possible combinations of polarisation states that we have. Why is this interesting to liquid crystals? Because essentially we use liquid crystals to manipulate these polarisation states. Remember, my liquid crystal has a director, and that director relates to essentially some anisotropic properties. I can use that anisotropic properties which are related to the shape of the molecule to control the light in a constructive fashion. So for instance, water, just isotropic, rather boring. I try and write in any direction. I see the same refractive index. Doesn't really do anything terribly exciting for me. Whereas I have something like calcite or our other liquid crystals, they have a particular molecular structure such that when light electric field passes through in different directions, they will have different interactions with the molecule. Sometimes they'll vibrate in vicinity with the molecule, sometimes they'll vibrate orthogonally to the molecules, and therefore they see different refractive indices, and therefore they propagate in different ways depending on the orientation of the light. And that's what we can use Jones matrices for. They give us a very powerful way of understanding these properties. And you've seen this demonstration before. A calcite long is essentially a crystal structure which has this rhombic lattice. And you can see here a row of dots in the background of a piece of paper, whereas when they come through at the front of the calcite crystal, some of the dots are still in line with the originals, and some of them have been shifted by a particular amount. And that relates essentially to the Snell's law, the refraction at the boundary. One of them propagates at one angle, one of them propagates at a slightly different angle. This is about a 10mm thick piece of crystal. Therefore, when they come out from the other side, they're effectively leaving the crystal from different places, and therefore I see this displacement from the different polarisation directions passing through the crystal. That's a piece of calcite, not terribly exciting because all it is a solid. If I replace this with a gooey mush and a liquid crystal, then I can start to manipulate that gooey mush, and I can therefore change that birefringent property. So, anisotropic properties means that if I have a vertically aligned electric field, it sees one refractive index, which is called NE for E for extraordinary. And if it sees the horizontal, it sees a different refractive index, N0, and that's N0 or NO for ordinary. So extraordinary and ordinary axes of refractive index. And as the light travels through, remember refractive index is the ratio of the speed of light in the material to the speed of light in the vacuum. Therefore, this one will be travelling slower or faster than this one if these two NE are not the same. So as they travel, they're traveling at different speeds, and therefore one will overtake or follow behind the other one as it propagates through the material. We can use that to change the phase relationship with that phi factor. We can manipulate that phi factor by having one orientation travelling at one speed and another orientation travelling at a different speed. And that's all that engineers need to know about liquid crystals. They have these magical properties. Here's an example, there's some numbers. Here I have a linear state coming in. It sees NE in one direction, N0 in the other direction. They travel at different speeds. So when I come out the other side, one's got ahead of the other. And therefore now I've got a phase difference, stuff called gamma. And that phase difference gamma, which we call the retardance, is a function of three things. The thickness, how far it's propagated, T. The difference between the two refractive indices, the difference in the relative speeds effectively, NE and N0, that's often known as delta N, the birefringence of the structure. And don't forget, this periodicity is also very important. This relates to essentially how the wave is propagating through the material. A lot of people often forget that it's related to wavelength, so all these birefringent effects are actually wavelength dependent, and you've got to keep that in the back of your mind when you're dealing with crystals, because sometimes you want things to work over a broad range of wavelengths, and they don't, because this thing is wavelength dependent. So you've got to remember that lambda's in there as well. So here we go. Figure number 2. Name this state of polarization, where I have essentially gamma equals pi. Ooh, it's slowed down now. 774, come on, come on, come on. Those who 4B11 in this room should be racing through this. Is it left circular? Is it right circular? Is it 45 degree linear? Or is it spontaneous polarization? Just to throw you in another term, if you come across it with crystals, the term is spontaneous polarization. It has nothing to do with this kind of polarization. It has to do with the polarization of the electrostatic dipoles of the system. And it's one of the most confusing things that you come across with crystals when they kind of recycle the terminology. So you get polarization of light, you get polarization of molecules. Like, please give them different names. So the engineers can't cope with these multifunctional descriptions. Time on. Who is right? Oh, that was surprising. I must admit I'm slightly disappointed. But never mind. Obviously there's some chemists in the room. I apologise. The 20 of you who got this one, puck out spot on. The really hardcore would say there's a plus 45 or minus 45. I haven't mentioned sign conventions here because I haven't got the time or the bandwidth to discuss it. But if I have 2 bays that start off in phase, and I shift them by pi, and I get another linear state of polarization. Just flip over the other way, actually it will be minus 45 under the terminology we have. Those of you that turn left and right circular, I'm sorry, still one. A good guess. Die. Click on the back screen. Yes. In mathematical terms, these are the Jones matrices for that process. If I have essentially a gamma retardation factor, that represents a phase difference between the 2 eigenstates. I can either have a naught here and e to the j gamma on one side, or I can have minus gamma y2 and plus gamma y2. Either way, those 2 waves are being retarded with respect to each other by a factor of gamma. That of course assumes that your axes are lined up with your polarization states. If you have an incoming electric field at any angle to the axes x and y, some angle psi here, we just use a matrix rotation operation, and we get the arbitrary angular version of the Jones matrix. So it has essentially 2 dependencies, one of which is gamma, the retardance, the other of which is psi, the angular displacement of the electric field vector to the x and y axis. And with those 2 parameters, I could basically do everything else in this lecture. I don't need to know anything else more complicated. That's all I need to know to understand the propagation of light. There is one thing I need to understand this further though, and that is I need to be able to analyse the direction of the polarization. Therefore I need some way of seeing polarization. And the easiest way to see it is to try and block out one of the 2 possible states. So we use a polarizer. A polarizer is basically, in the old days, urine, had the right sort of molecular structure. You stretch the molecules to form a particular direction of the dye in the urine, and then effectively absorb the electric field in one direction and pass the electric field in the other direction. And therefore I got a polarizer which could select one of the 2 eigenstates arbitrarily depending on its orientation. So here I have parallel polarizer with my light, therefore light passes through. Do note I've drawn the square as being a funny green colour. The reason why a funny green colour is because not all the light goes through. This line should be slightly larger than that one. There's a loss even associated with aligned polarizer with the light, because this will still absorb some of the light as it passes through. However, if I have it orthogonal, then the 2 are essentially opposed to each other, so I have no resulting polarization state. So I can now put a polarizer in front and see whether I've got this state or this state just by rotating the polarizer and seeing what comes out the other side. And that's the basis of all displays. All we have is essentially is a way of controlling this polarization and a series of polarizers, usually crossed, which then dictate how the light propagates. Once again, Jones matrices style, that's a polarizer aligned to the XY axis. That's a polarizer aligned at any angle to the XY axis. They can be either horizontal or vertical just by changing what psi is. Therefore, all of my polarizers are covered in this particular Jones matrix here. So we put this all together and we have now an analytical tool for understanding how light propagates through these systems. This is why Jones matrices are so powerful. I start off with an input direction of light. Now remember, my light goes this way. So here's my input, vertically polarized light. So here's my input here, the matrices go the other way. So here's my input light here, that's the vertical component. Here's a vertical polarizer, which looks like this. Here's a half wave plate. A half wave plate means it has a retardance of gamma, so gamma equals pi. And I've oriented it at 45 degrees to the axis, so psi is 45 degrees. Put that into my nasty matrix you saw previously, you get back to the Jones matrix of a rotating wave plate. Horizontal polarizer, like so. And lo and behold, what do you see? You see that even though these two polarizers are crossed, and therefore no light should propagate through, it should just be 0, 0 at the output here. What we actually get when we multiply these matrices together is in fact all of my light coming through with a arbitrary phase lag. That arbitrary phase lag is with respect to the original waves. It doesn't really matter what that phase lag is. The minus j is really just there for decoration. I have all of my light coming through the system, and that's because my half wave plate has effectively rotated the direction of the polarization and allowed it to pass through these cross polarizers. And that's what your display does. Every time you put your display on, there's a nice white background. What you have is a pair of cross polarizers. You have a liquid crystal in this particular geometry here. So it's providing a 45-degree rotated half wave plate. And lo and behold, we're getting all the light through the system in a really nice bright state. If I rotate this so it's up, the axis is pointing in this direction, then I now have essentially cross polarizers again, so I have my black state. So all liquid crystals do in my head is they sit in this gap here and they manipulate the phase of the light in some way to either pass or block the light through cross polarizers. And that's why Jones matrices are so powerful. They have this really quite important fundamental property. So now we can put together all those pieces and talk about optical modulation. I thought I'd put this in just for reference, so I'm going to talk about two particular liquid crystals which have interesting optical properties for me. One is the Electro-hydrodynamic, we've seen quite a lot of already, and one which you saw a bit of in Rob talk, which is on symmetric C, symmetric C star phase. I'm not going to go into between C and C star and all the complications of phase. What I'm interested in is how the two particular molecular structures can lead to interesting optical effects, particularly modulation. We already know this. We know that essentially the molecular shape of the molecules gives us a particular orientation, gives us a preferred orientation, gives us a statistical orientation, and therefore if we take something like a rod-shaped colorimetric liquid crystal, we can essentially see the molecules line up in the preferred direction, and therefore we can take a bulk crystalline effect from what is fundamentally a liquid material. So here's my general model for this. You can see it's a bunch of these funky shaped molecules represented as relevant ellipsoids. And they're all banging into each other statistically, but they have a preferred orientation in this direction here. So as Nigel described, we describe a director, and that director represents the average direction the molecules are pointing in. I'm really only interested in that direction. I'm not interested in where the molecules are, what they're doing. I'm just interested in roughly what direction they are pointing in, and also what their properties are. You can see from the modelers, we have arbitrary random isotropic at high temperatures. We cool it down a bit, we get this kind of one orientation order, where they're all pointing in one particular direction, there's no other orientation. And then when we get to the symmetrics, we have this common direction. We also have now these layers appearing, these order in this dimension, which shows we're heading more and more towards a solid crystalline structure. I'm just going to use these two as a very simple way of describing some of the optics of liquid crystals. In order to do this, we need to know one fundamental parameter of the liquid crystal. We need to know its optical anisotropy, or its birefringence. We need to know what NE and N0, or when there's the difference between the delta N, is for our material. That's pretty much all we need to know for our liquid crystal devices. So, very, very simple model for either of those liquid crystal phases. Here's my director N, and here's my optical indicatrix. Now, my optical indicatrix has two components: the extraordinary axis, which normally is the longer axis of the molecule, doesn't have to be, and my ordinary axis, which is normally the shorter axis, once again, doesn't have to be. And my birefringence is just NE minus N0, so my delta N. That gives me my gamma with the thickness of the cell and the wavelength, and that gives me the retardance, the ability to flip the polarization in my joint matrices. That's all there is to it. That is the limit of the maths in this presentation. You'll be happy to know. The second thing I'll mention in passing is that if we just have a fixed molecule in a fixed direction, not terribly exciting, what we need to be able to do is make it move. And we've seen from Rob, you can squash it, squish it, cook it, bang it, whatever, smother it in gas, honey, and it will move in some way, shape or form. However, more importantly, these molecules usually have some sort of electronic structure, and we can use that electronic structure to actually manipulate the molecule by applying an external electric field. We saw magnetic fields as well. Magnetic fields are quite difficult to control, whereas electric fields are relatively easy to control with electronics. We tend to use electric fields to manipulate the direction of the molecule. Once again, we don't need to know much about the molecule. In fact, I don't need to know what these permittivities are. I've just put them in to show them that they're there. And they don't have to be long actors, short actors, they can be different magnitudes to each other. What I want to know is roughly somehow in the molecule, what is the polarity of it in terms of its charge properties. And that could be an AC polarity where I apply an alternating field, and that sets up this induced dipole, as in the case of a pneumatic, or it could be a fixed electronic orientation, which comes from the chemical structure of its crystal itself, as you see in this metric, where you have essentially a fixed dipole in the system. Either way, it doesn't matter. All I care about is it has, by some means, a plus end and a minus end. Therefore, I can apply an external field, and I can manipulate the bias. So here's an example of a liquid crystal modulator. I have molecules pointing in one direction. Ne is now pointing this way. Here's my applied electric field, so therefore the molecules form an equilibrium state like so. I reverse the electric field and polarity, and what happens is that those dipoles now interact, force a torque on the molecule, make it rotate. It's a nice liquid, so it does so. And my Ne is now pointing in a different direction. Here's my light coming from above through the molecular structure. Here's a really sticky question for you. Name that modulation. Is that an example of pure phase only modulation? Is it purely intensity modulation? Is it fully complex phase and intensity modulation? Or is it frequency / wavelength modulation? What do you reckon? Come on, 33, let's squeeze some blood out of the stone. Keep clicking. Remember, E is not an option. 42. Any more drinks? Or 48 last time? There's 6 people that can't commit, and it's really depressing. Who pushed E? Too late. Should have said. Whoa, interesting. That's good. That's not bad. That's a good answer. I'm very pleased with that. Because, yes, you are right. As it stands, I've basically not given you enough information to really describe this. So as it stands, I'm a light lit crystal, therefore all I can do is retard the light due to that refractive index reorientation. What I'm doing is I'm rotating that Ne. So all I'm doing is changing the retardance of the two waves passing through the system. At best, that can only change the phase of the light. When you could argue in a more complicated way that it's also complex phase and amplitude, but it certainly isn't purely intensity modulation. Why? Because there's no polarizers. You've got to have a polarizer in the system. You've got to have something to block the light to give you that dark state. The only way you can get a dark state in these sorts of systems is if you block the light in order to prevent it from getting through to your output. So here I have no blockings, therefore all I can do is play around with the retardation. You could argue fully complex if you took into account diffraction and other more complicated effects going on with these waves as they pass through. But it certainly isn't purely intensity, and it certainly isn't, although it could be, if you look at the wavelength, I didn't say anything about the wavelength of the light, it could be wavelength by the wavelength dependence of the birefringence, sorry, of the retardance. Good answer, I'm pleased. So, in the liquid crystal device, I have essentially a pair of electrodes which allow me to apply an external electric field. In this case, I've got no field applied, therefore the molecules stay in that orientation, so they C and E. And I apply a field, the molecules rotate into an equilibrium position, and now I see in naught. So I get two different retardances. Therefore, I put them between cross polarizers and I design the cell gap so that in this direction I have a bright state, in this direction I have a dark state, and jobs are good. Do remember, it often depends on the polarization of the light. This effect will only work if this electric field is polarized parallel to the molecules. If the electric field is coming out of them, so the electric field is going this way, what refractive index does it see? It sees the short axis of the molecule, it sees N naught. So therefore, if light is coming out of the plane, so the electric field is this way, it sees N naught here, and it sees N naught here. So there's no modulation at all. So this is a good example of an effect that is polarization dependent. You come across lots of things in life that are polarization dependent, and that's one of the big criticisms of liquid crystals. Every time I go into a telecommunications discussion with someone about optical switching, they always say, is it polarization independent? And I go, well, actually no, it's not. Because if light comes out of an optical fibre, I don't know what its polarization is, it might just happen to be orthogonal to this, in which case I get no effect, or it might be parallel to this, in which case I get full effect. So polarization dependence is something you've got to keep in the back of your mind as whether it's a good thing or a bad thing in your application. It's nearly always a bad thing, unfortunately. So very quickly, I'm going to talk about the matrix. These have the lowest order. Two properties I get from them as a device person. They are continuously variable. I haven't got time to describe why they are that case, but they have essentially the ability to reorient in any particular orientation of the electric field. However, as a result of this and their particular fluid properties, they are very slow. That's one of the holy grails of liquid crystals for displays, is to get that 1 millisecond or below response time for a pneumatic. So I can make one of these puppies do 1,000 frames per second plus, then I can make 3D actually look convincing and not make you want to throw up all the time. Then I can do other things with the display, switch the backlight off, all sorts of clever things, which then allow me to increase and enhance its performance. And that's one of the things that is essentially driving the display industry forward at the moment, trying to find this mythological material that has this high-speed response. Optically, it's very simple. I'll just skip that one. This is one more useful. If I have a positive, remember I mentioned that my permittivities can be either way with respect to the axis of the molecule. I apply electric field. Is that the wrong way around? That's wrong. That's actually the other way around. My diagram was hang on. Ha! Voiced by my own guitar here. I turned off animation. This is a slide that required animation. Oops. Bugger. Okay. Let's just see if now I can't recover this very easily. I can. Rest your butt cheeks for a minute. This is how it should look like. Here we go. Not so bad now. So here's my positive dielectric anisotropy. So my delta is greater than 0, so my long axis is longer than my short axis permittivity. And I go from essentially a planar aligned liquid crystal with the molecules are parallel to electrodes, apply a field, and then we orient into this what's called homeotropic or vertical position. And that's a good example of what's used in many, many display devices. However, I can also get negative dielectric anisotropy, where essentially delta x1 is less than 0, it's negative. That means my long axis is shorter, permittivity is smaller than my short axis permittivity. That means the molecules act in reverse, and therefore I can switch from the homeotropic state, where they're all vertically aligned, into a planar state. And that's very useful for the optical viewing characteristics of the crystal. It's also slightly faster, so you get a quicker device by using these negative dielectric materials. We see van, hand, WAN, pop, pan, umpteen different types of display technology which have used this effect, these materials, to speed up and increase the viewing angle, particularly of your liquid crystal display, because this has a much better viewing characteristic than going the other way in the system. It's difficult to describe without half an hour lecture on Poincare spheres, but it's a very useful property. So that's negative dielectric anisotropy, and gives us van. Now I've got loads of different things, here we go. Now I'm stuck with animations again. So here's my model for this. Quite simply, I have my molecule Ne and N naught. I have it now oriented to the surface by some angle theta. That gives me some refractive index as a function of the angle theta, which is described by this function here, which is a function of Ne, N naught, and theta. And that means my retardance gamma is essentially variable. It's now a function of that theta. So I can vary my retardance, and I vary theta, remember, by adding or decreasing the electric field in order to repel or attract the molecules in some particular way. So my electric field applied controls the angle, and the angle controls refractive index controls retardance, and retardance controls the contrast of my display, or the retardance of my system. And here's a really vintage plot from ancient days, showing essentially retardance as a function of RMS. Well, it's RMS because it's a induced dipole, and in this particular case, here's my Friedrichs transition. And one thing that Tim didn't mention yesterday is that nobody knows how to spell Friedrichs in the world as far as I'm aware. And here's his threshold. Here's my gamma ever increasing as I increase the field, so I'm getting more and more retardance between the waves. And this can be anything up to sort of 20 pi, depending on the birefringence of your material and the thickness of your cell. And here's my intensity plot. As I go through, as I put it between cross polarizers, I go from a quarter wave plate to a half wave plate to a zero wave plate to a quarter wave plate to a half wave plate. Every time I go through one of those transitions, I go from a light to a dark. So I go bright, dark, bright, dark, bright, dark, bright, dark as I increase. So each one of these blips represents a 2 pi variation of this retardance. So here's the ultimate. Take a question. Why does the intensity of this plot, why does this here not go to 0? Cross polarizers, surely it should be dark. Click now. Is it A, too far to walk? Because the molecules are lazy and don't like walking. Is it because the liquid is not symmetrical in some way? Is it because it can't point fully upwards? Or is it because the molecules, and the molecules are a very special example of molecules, the surface don't move? This is an easy question. This is like just a 101 question. We've got 10 years to figure this one out. The battery's getting flat. Well, 43, come on, we're out there. Come on. Nope. Oh, yes, he did. 43 made a difference. Ah, yes, excellent. I'm glad to see it. Well done. Most of you got it. 24 of you got it because essentially the liquid crystal molecules cannot move easily from the surface. And actually, there was a bit of a hint in this presentation, because if we just get rid of that for a second, come back around to the backspace, animations. If you look here, you can see that as I apply my field, which you want the other one really, this one, when I apply my field to go from planar to hypertropic, you can see the molecules in the middle are winding vertically, but the molecules on the surface are still stuck to the surface. And that's because there is actually a surface force attracting the surface, anchoring to the surface, and we have to essentially push them off the surface, and we haven't got enough energy to do so. They'd rather be on the surface. And that's one of the things the modelling tells us, that how this structure, how this profile forms, and therefore how we can optimise this process to give us the best possible contrast in my system. So I need to compensate for that in some way in order to get this drop down to 0, so I get 0 light from my system. So yeah, exactly, answer D, the molecules. So we also have twisted magnets. I'm not going to say much about them now because we haven't got time, but basically you put a twist and it gives you a better viewing characteristic and a better electrostatic effect. That purely just lifting the molecules off the surface is slow and rather tedious. If we put some twist into it, we change the fluid properties of the liquid crystal in a way that gives us more of a ping and more of a response. And we can also use Morgan guiding to give us a better viewable electrostatic effect. So it's not just purely birefringence, it's now also some wave guiding effects as well. And if we twist more 180, 270 for super twist, and that gives even more of a ping, gives even more complex modulation. However, it makes the whole system more complicated to analyse. I can still use Jones matrices, but I have to use a thing called Conforti's technique. It's essentially a method where you slice this plane into different, like many thin wave plates, and you add them all up as a sort of a geometric series, and you come up with an average wave plate that represents the entire twisted structure. So it's not a complete disaster, but it is a lot more complicated than just doing a simple birefringence. I'll skip that. My final bit, I'll run out of time, but I'll just very quickly mention. We can also describe other ferroelectrics. I'll skip to, I won't go through all the boring electro-optics of basically one of the reasons that ferroelectrics are interesting is because they have this or they can be designed to have this extra dipole which sticks out the side of the molecule. So before I had a plus and a minus end to my molecule, now I've got a bonus electric dipole from the chemistry pointing to the side. That is the thing that's called spontaneous polarization, or PS. It's not the same as the polarization of light, that's the polarization of this dipole. And that means I've got essentially, think of my molecule as being this rod-like structure. I've got this handle sticking out the side. And I can grab hold of that handle and use it to rotate the molecule in a more dynamic and fundamental fashion. That's why ferroelectrics have better speed properties, among other things. I haven't got time to describe this in detail. One of the problems when you put these things into a bulk, these dipoles interact with themselves, each other, and therefore they repel each other because they are electrostatically charged, and therefore across a particular distance you can essentially get no electro-optic effect. So what Clark and Lagerwald came up with in the 80s was a very clever way of essentially engineering this by making the cell very thin. Remember, we have those surface anchoring forces to prevent the molecules from being rotated. Well, I can actually use those surface anchoring forces to attach the molecules in a very fixed fashion, and I can use that dipole like a lever to move the molecules backwards and forwards within the cell. And as a result of that, I get what's called surface stabilized liquid crystal effects. And optically, that means something quite simple. I have my molecule here, here's my dipole sticking out the side, here's my applied electric field, that's in equilibrium. I reverse the electric field, what happens? I'm no longer in equilibrium, my dipole has to move, my lever effectively turns the molecule round, and in doing so I rotate it, when these liquid crystals are tilted, I rotate it through its tilt to give me a different orientation of my molecule, but now through this angle theta. One of the plus sides is I can make this bistable, I can make it stay in these two states in a stable fashion. Minus is it only have two states. I can't stop it anywhere in between. It's got such strong elastic forces, it can either be this way or it can be that way, but it can't be in the middle. It just doesn't want to do it. It either wants to be one of those two states. So it's only a binary electro-optic effect. However, from the engineering perspective, what do I have here? I have NE and I have N0, and I have the ability now to rotate it, not like a pneumatic, where my liquid crystal starts like this and goes like that. I now have my liquid crystal starting like this, and it goes like that. So I'm rotating it in the plane of the cell rather than out of the plane, as we saw with the pneumatic. This is a different electro-optic effect. I can still use my Jones matrices to analyze it in a simplistic fashion. I'll skip this bit. Here's my Jones matrix, remember, for my wave plate. Whereas with the pneumatic, I was manipulating gamma with my electric field. Here now, I'm manipulating theta with my electric field. That's the difference between in and out plane electro-optic effects. And just to quickly show you, here I have a vertically polarized state. Here I have a pixel where my NE is parallel to that state. I'm going to polarize it also parallel, so everything is parallel. So light passes through, and that's what my Jones matrix tells me. Light comes in, light comes out. Woohoo! I then apply electric field, my molecules then rotate through theta, so NE is now rotated by theta. So now I've got different axes, same light coming in, same polarizer coming out. Everything else has not changed, what it does is apply a field to the pixel. And now that means here's my first state, here's my second state, more complicated maths, more complicated rotated matrix, more complicated system, still not only vertically polarized light, but now I've got this extra phase term here associated with the rotation of theta. Once again, I can optimize that, and to cut the long story short, I can say if I want one of those two states to be 0, I'll take this one and make it set it to 0, and I do that if I set the condition such that I have a half wave plate, so I have a gamma in the thickness of pi, and I have a switching angle by theta of 45 degrees. That gives me a very effective binary intensity modulator. You can have a 10,000 to 1 contrast ratio if you get these two parameters right. So you can make very, very high quality, very high speed modulators, and you can analyze the whole thing using simple Jones matrices. And finally, I can also do phase. I'm just going to skip to this very quickly, and I'll just show you the final picture. So here's my two possible states. I now have a vertical light. I have my axes rotated by half the tilt angle, theta on 2. I now have a horizontal polarizer. As I switch it with the field, I go to the other side of the axis by theta, so I'm now minus theta by 2, same polarizer, same input light, which, to finalize, there's state 1 Jones matrix, there's state 2 Jones matrix. I've still got horizontal light. What is the difference between that and that state? The only difference between those two states is the sign. So what I've got is two states which differ by a factor of -1. This is a +1 state, this is a -1 state. I've got a perfect binary phase modulator. All I have to do now is choose gamma and theta to be 1, and therefore I get essentially just a binary phase system. So the ferroelectrics can be both intensity and phase modulators, just depending on how you orient them and how you design them. You can also you can do other things I don't have time to describe now. They're a very versatile and useful way of getting access to an optical system, and you can analyze it using this very simplistic view of the crystal molecules, purely as birefringent objects with different orientations, which can be varied by electric field. I'll stop there.
I think we're going to move on.
Yep, no worries. I can see Randy in the back there.